Here we are introducing our project topic called 3D volumetric display. Since we are living in a 3D physical world, the information we get from 3D images is much better than 2D images. 3D volumetric display is mainly classified into two: swept volumetric display and static volumetric display. In static volumetric display, the image is generated using a static 3D space. In swept volumetric display, the image is generated from the motion of 2D surface of emission. Here a swept volumetric display with a rotating LED panel is designed. Here we are using the phenomenon of persistence of vision to achieve slices of static images to eventually get 3D images. This is in sync with Arduino board, which controls the LED array. Here we are using a motor to integrate the LED array and the Arduino board. This is an overview of our project.
Now we are coming to the components or parts required in this 3D volumetric display. First comes to the microcontroller. The microprocessor is a fundamental component of the device. Its task is to run the Arduino program, which identifies those LEDs that need to be illuminated. Here we use ESP32 Room32 Node MCU module, which is powerful tool used for various IoT purposes with integrated Wi-Fi and Bluetooth, which help us to control the microprocessor wirelessly. It consists of 26 GPIO pins, out of which 16 pins are connected to the LED array. The microprocessor can be controlled using a DC power source. Therefore, a 3.7 volt Li-ion rechargeable battery is used. It's compact in size and weight less than 50 grams, making it light and easy to incorporate on the rotating mechanism. Next we are coming to the LED array. A dot matrix common anode red LED display is used here. The function of LED display is to show the image, and here it show a 2D image after rotational sizing of the 3D image that need to be shown. The diameter of the LED is about 3 mm with common anode configuration, and it consists of total 64 LEDs with 8 LEDs in a row, and it emits red color. It has a length and breadth of 32 mm with a total weight of 400 grams. This LED is placed with the frame so that it is properly fixed to the motor without any freedom of movement, and it will rotate accordingly to the speed of rotation of the motor. Next we are moving to the frame. This frame is actually used to fix the LED display to the motor. The plastic obtained from renewable material such as polylactic acid PLA is using here. The 3D printed display frame is connected to the threaded shaft of the motor, and the LED array is connected with the frame. The size of the display frame is about 100 cm length. The display frame holds the LED array, and hence the rotational sliced image will be properly rotated with the motor without any vibration, and hence the persistence of vision is achieved. And next we are moving to motor. For persistence of vision, the setup is required to rotate at an RPM of 1800 in order to achieve 30 fps. Speed above 1800 RPM is also applicable. Actually, here we use the motor of a pedestal fan due to the unavailability, and we removed the wings of the pedestal fan and placed the 3D display with the frame here. And this motor works at 220 volt, and it is able to achieve 1800 RPM. Now we are moving to the power supply. The power required for the microcontroller, that is ESP32 Room32 node MCU module, is satisfied using 9 volt high watt battery having a capacity of 2500 mAh, whereas the power for the motor is given through AC or DC adapter.
Coming to the details of work. So in our project, we have adopted the concept of persistence of vision. So according to persistence of vision, an image persists on our eyes for about 1 by 16th of a second. So here we require to display 3D images. So as a basic step, what we do is that we take the two-dimensional slice of that image. For example, in case if you want to display a 3D image that is a sphere, the 2D image corresponding to that will be a circle. If you want to display a cylinder, the 2D image corresponding that would be a rectangle. And in the case of the cone, it will be a right triangle. Now, this 2D image is rotated along its vertical axis, that is through its center, at an RPM of 1800. So this 1800 RPM actually corresponds to 30 Hz, and at this speed persistence of vision occur. The required 2D image is displayed on an LED array. The LED array is of an 18:8 matrix which consists of 64 LEDs. So this LED array is designed in such a way that there is a common terminal corresponding to each row and each column. For each row, there is a common positive terminal known as a common anode, and for each column there is a common negative terminal known as a common cathode. Therefore, a total of 16 terminals are provided to the LED array through which we could control it. For example, if we want to light up the LED D10, we must provide 3 volt to pin 2 and ground the pin 10. So basically, if we want to light up a single LED, we must give a positive voltage to the common anode terminal and we should ground the negative terminal corresponding to that LED. But this leads to a problem. For example, if we want to simultaneously light up both LEDs D1 and D10, in this case, we will have to provide positive 3 volts to terminal 1, that's pin 1 and pin 2, and ground the pins 9 and 10. But doing this will instinctively turn on the LEDs D2 and D9, which was not desired. So, in order to avoid this problem, we are introducing multiplexing. According to multiplexing, only one row will be powered at a time. Here, first the power is provided to the pin 1 and the cathode terminals are turned on and off one by one according to the binary data given in the program. Once all the LEDs of the row 1 is checked, the power to row 1 will be discontinued. Now the second row will be powered. So in this manner, all the rows are powered one at a time until the last row is powered. But this process occurs at a very high speed so that human eye cannot differentiate between the state of LEDs among different rows. So the eyes will perceive that all the LEDs are light up together, although the LEDs are turned off and turned on at different times. So this is the basic mechanism of how we control the LED array. Now the programming part is done using the software Arduino IDE. So here first we assign 8 rows and 8 columns corresponding to terminals of the LED array. Each terminal of the LED array has an corresponding terminal for the ESP microcontroller. First of all, the image to be displayed, that is the 2D image, is stored as binary numbers in an 18:8 matrix. The logic is that if the points corresponding to which the LEDs needs to be light up are given the value 1 and those that are not to be light up are given 0. Consider the simple example of an 18:8 matrix where we are required to display a letter I of the alphabet on the LED array. In this case of the 18:8 matrix, we will give 1s in the positions where we should light up the LED so that the final output will become the letter I. And the positions at which the value is 0, the LEDs will remain dim. Now comes the main part of the program, and this is where the multiplexing takes place. Here, first row of the LED array is initially initiated. Then the program checks whether the value of each element of that row is 1 or 0. If it's 1, that particular terminal of the column will be grounded, which will light up the LED. Otherwise, if it is 0, it will be turned off. This program will iterate 8 times, that is for each row, and once the 8th row is initiated, the loop again repeats the same thing. In this way, all the 4 figures, that's the 4 2D images, will be displayed alternatively. Now, this program is fed to the microcontroller, that is the ESP32 Dev module. Coming to the setup, the 3D printed module is fastened to the shaft of the motor. The module consists of a platform where the LED array is planted and a box where the battery and the microcontroller is placed. The entire setup is rotated using the motor at a speed of 1800 rpm. The LED array will display the predefined 2D shapes like the rectangle, triangle, sphere. Since the rotation is at very high speed, persistence of vision occurs, resulting in voxel formation, which eventually creates the three-dimensional image corresponding to the 2D images, namely cylinder, cone and sphere.
Coming to the results and conclusion of our project, we see that the images we created had lesser opacity as well as lesser resolution. This may be due to the jerking from the motor as well as the lighting conditions where we recorded while we were recording the clip. From these clips, we can conclude that perceptible voxels were created at predefined locations. The theory for creating 3D models using persistence of vision is true. So if we had a bigger budget to work with and move forward with, we could have used a much better microcontroller, that is for example an FPGA board, and also employ some better image processing techniques to achieve a real life imagery. If we are able to achieve this modification in our current design, then we can realize some sci-fi concepts like holocalling, that is a type of video call using holograms. Therefore, in conclusion, we can say that all the objectives that we laid down was achieved and we were able to create voxels. This is the most important part of creating a 3D hologram. Thus, the technology that was only alive in pop culture is now one step closer to becoming a reality.